Namaste. Welcome once again to Murali's World of Physics. In my previous video, that is the first part of the video on the physics and applications of accelerators, I had explained the basic principles of accelerators and then discussed the electrostatic and radio frequency linear accelerator. In this second part of the video, I'll be discussing about the cyclic accelerators, their principle of working and details about the main components, etc. And finally, some of the important applications of particle accelerators. In the previous video, we saw that in a linear accelerator, as the ion energy increases, the drift tubes become longer and longer. Therefore, when we go to high energies, the linear accelerator becomes quite unwieldy in length. Is there any way to keep the size of the accelerator compact without sacrificing on the available energy? So one solution obviously would be to bend the trajectory of the entire beam into a circular trajectory to start with. That means make the metal drift tubes into semicircular shapes and force the ions to travel along the axial direction of this particular shape of the beam pipes. The question is, but how? It would be, well, the size of the accelerator would be compact if we bend the total beam pipe into a spiral shape like this. But how? Well, here comes the magnetic field to our rescue. That means let the ions drift through a magnetic field perpendicular to the direction of motion. So naturally, the ions will move in circular orbits. Now, let us understand the working of the magnetic field in this following animation. Now, this is the straight line trajectory of a particle moving in the linear accelerator. And now we apply the magnetic field, whose field lines run perpendicular to the plane of the trajectory. So we can see that the trajectory gets bent into circular trajectories of increasing path length. And thereby we get what is known as the cyclic or circular accelerator. The foremost example being the accelerator which is known as the cyclotron. Now here acceleration is provided at the end of each semicircular part of the trajectory of the ions. The successively increasing path length is automatically taken care of by choosing a semicircular trajectory of the appropriate higher radius. So this will ensure that the ions reach the next accelerating gap exactly after half the period of the RF. The first accelerator of this type was developed in the early 1930s by the American physicists Ernst Orlando Lawrence and M. Stanley Livingston. These are the two scientists who developed the cyclotron. In the actual cyclotron, the individual semicircular drift tubes are dispensed with. Instead, two semicircular hollow metal enclosures called Ds are used. These are the two Ds. These are hollow metallic enclosures. And the ions will be traveling inside within these two Ds. So the small gap between the two Ds act as the accelerating gap in each semicircular traverse of the beam through the accelerator. So the two Ds are connected to the high frequency voltage source. Then we have a magnetic field which is perpendicular to the plane of the Ds. Then once the particles are accelerated completely, they are extracted outside of the accelerator by means of deflecting electrodes. So this is a cutaway view of the accelerator. We have the north and south poles of the magnet. Then this is a section of the two Ds. The ion source is kept in the middle here, and therefore, of course, the ion trajectory will be perpendicular to this plane in this direction. The motion of the ions of mass m in the circular trajectories under the influence of the magnetic field is given by the equality of the centripetal force and the magnetic Lorentz force. That means m square by r is equal to qBV into V, where r is the radius of the semicircular trajectory. Here V is the velocity of the ions and r is the radius of the trajectory. The angular speed of the rotation is omega is equal to v by r, which from the above equation this will be equal to qb by m. And therefore the rotational frequency, which is known as the cyclotron frequency, is f is equal to omega by 2 pi. So that means qb by 2 pi m. So we see that this is independent of the radius and velocity of the particle, and therefore independent of the particle's kinetic energy. That means all particles with the same charge to mass ratio rotate around the magnetic field lines with the same frequency. The period of the circular motion is simply t is equal to 2 pi m by qb. After receiving an acceleration from the RF field in one gap between the two Ds at a particular radius r, if the ions reach the next gap again after a time exactly equal to the half of the above time period, the field would have reversed in polarity and the ions will be in phase to receive the next acceleration. Therefore, the ions will get accelerated in steps at successively higher gaps, thereby increasing their velocity and energy and moving in increasingly larger radial trajectories until at the periphery of the accelerator they are deflected out to fall on a given target. The kinetic energy of the particles at the trajectory of radius r is given by E is equal to half ma square, and substituting for V from the earlier equations, this is equal to q square b square r square by 2m. And this is independent of the voltage and frequency as well as the number of turns. For a given ion, this energy depends only on B and R. The maximum energy that can be achieved is limited by radiative energy losses. That means as the particles' energy increases, these particles being charged, they emit radiation and thereby lose energy. So therefore, the higher the energy, the larger will be the energy loss by these radiative processes. Now this process is known as Bremsstrahlung emission. So therefore, the higher energy will be limited by energy loss because of the Bremsstrahlung emission. Any further energy increase stops when the energy gain in one turn is compensated by the energy loss due to radiation. There is yet another serious problem with cyclotrons, that is with regard to the relativistic mass increase of the ions. Now our frequency is f is equal to qb by 2 pi m. Thus as the energy increases, mass increases, and therefore the cyclotron frequency f will decrease. And therefore the ions will be unable to stay in phase with the RF to receive the appropriate acceleration. So they will fall out of phase with the RF. If you want to keep the ions in phase with the RF, there are two methods. The first one is the RF frequency should be continuously reduced to keep pace, or otherwise the magnetic field strength should be increased proportionately as the particle energy increases. So the compensation can be done in both these ways. In a synchrocyclotron, the RF frequency is continuously reduced as the ions get accelerated and traverse larger radius orbits. This is also known as frequency modulated cyclotrons because the frequency is varied. Now here we can see the synchrocyclotron. Here only one D is used instead of the two Ds. The RF is applied between the D and the ground point. So this is the ground terminal. The magnetic field is kept constant, whereas the RF frequency is continuously decreased as the particles move out into higher radius orbits. In the synchrocyclotron, RF modulation is usually performed sinusoidally. The repetition rate spans from several tens to several hundreds of hertz. Therefore, a pulsed beam of particles is extracted from the ion source at the center of the cyclotron in a typical period of several tens of microseconds, and then accelerated by this FM RF. FM RF means frequency modulated RF accelerating field. During the acceleration of the one pulsed beam, the next pulsed beam cannot be captured or accelerated. It must wait for the next cycle. That is natural. Therefore, one drawback of the synchrocyclotron is that the average beam intensity is very small, as small as 10 raised to minus 3 times that of a fixed frequency cyclotron operated in DC mode. The second method of overcoming the difficulties arising from the relativistic increase in the accelerated ion mass is utilized in an isochronous cyclotron. Now what does isochronous mean? That means equal in duration or interval. Here the magnetic field is increased as the ion energy increases so that the frequency remains a constant. The synchrotron is another descendant of the cyclotron wherein the strength of the magnetic field increases. That means that is synchronized with the energy of the particles to maintain their orbital radius constant. Here a torus shaped tube is used instead of the Ds of a cyclotron to contain the ion beams in a fixed radius trajectory. So here the trajectory of the beam has a fixed radius instead of being a spiral. In the synchrotron, the components can be divided into different sections. The acceleration of the particles and the bending of the particles path can be split, meaning that the accelerator, as opposed to being circular, can be slightly oval shaped or like a square with rounded corners. So this is a typical schematic diagram of a proton synchrotron. So here we have 4 magnets at the four corners of the rectangular trajectory, and I have shown 2 accelerating stages. So the beam is injected at, let's say, this point, then with a certain initial energy, and the magnet M1 bends the beam like this through 90 degrees and then enter the accelerating stage. Then their energy is increased, they enter the magnetic field in M4, they get again deviated through 90 degrees and then enter another accelerating stage, and so on. And finally they will be deflected at the point D and they hit the target. A particle in a synchrotron will be accelerated in the accelerator gaps while traveling along the straight section as they would be in a linac. The particle's path is then curved by a magnetic field, taking the particle to another straight section where it is again accelerated, and so on. So the particle will go round and round the accelerator, gaining more and more energy with every revolution. The principle of the synchrotron was invented by Vladimir Wechsler in 1944. Macmillan constructed the first electron synchrotron in 1945, arriving at the idea almost independent of Wechsler. The first proton synchrotron was designed by Sir Marcus Oliphant and built in 1952. The accelerating sections in the synchrotron are called resonant cavities. Here, standing RF waves are generated with their electric fields directed along the axial direction. So that is why the particles gain energy along the axial direction. The typical energy gain per turn is about 1 keV. So therefore the protons on the average perform 3 or 4 million revolutions around the central stable orbit, covering a total distance of about 100,000 miles before acquiring energies in the BeV range. The largest proton synchrotron, also the largest particle accelerator in the world, is the 27 km circumference Large Hadron Collider LHC in CERN. The maximum energy of the protons is 7 TeV. Effective relative energy of the colliding beams would be 14 TeV. Here actually we have 2 colliding beams. The very important discovery of the fundamental particle responsible for the mass of other particles is the Higgs boson, and its discovery was using the Large Hadron Collider a few years back. Now this has been called the God's particle, and this discovery has been one of the revolutionary events in the history of particle physics. Another important type of accelerator is the betatron for electrons. The cyclotron is not at all suitable for accelerating electrons. The reason being that even at very moderate energies of 1 MeV or so, the electron velocity approaches the velocity of light. Hence, the relativistic mass increase becomes so serious that the electrons go completely out of phase with the accelerating RF field. One solution is the betatron, devised in 1940 by Kirst. Essentially, this is a type of transformer with a torus-shaped vacuum tube, which is called downut, as its secondary coil. The alternating current in the primary coils accelerates the electrons in the vacuum, and they are forced to move around a circular path of constant radius by means of a magnetic field. The constant radius and frequency conditions are maintained by increasing the magnetic field as the electrons gain energy and thereby increase their mass. The downut, of course, is placed between the pole pieces of an electromagnet with specially shaped pole pieces. This is to give a particular type of magnetic field. The magnet provided with a substantial amount of iron as core and generates a strong magnetic field in the central space. The electrons produced by means of a heated filament are given a pre-acceleration to about 50 to 70 keV with a velocity of the order of half the velocity of light, and they are injected into the downut at a time when the primary current through the magnet coil starts to increase. So this is a cutaway section of the betatron. We have the pole pieces of the magnet, the downut shaped vacuum chamber. These are the coils which energize the magnet, and these two dots represent the trajectory of the electrons. The magnetic field has two effects. One is the increasing magnetic field induces an EMF along the axis of the downward, and it is this induced EMF which accelerates the electrons. The magnetic field also bends the electrons into circular trajectory. The increasing trend matches the relativistic mass increase to keep the radius of the trajectory a constant. Now let us see what is the condition for achieving the correct action of the betatron accelerator. If phi is the magnetic flux, then the induced EMF will be d phi by dt. Therefore, the energy gain per turn will be E times B, that is equal to E d phi by dt. The tangential force will be W by 2 pi r, because the work done in one cycle is W and the total path length is 2 pi r. So therefore, the tangential force is W by 2 pi r. For the circular path in the magnetic field B, the electron momentum is given by P is equal to EB r, and therefore the force can also be represented as dP by dt. So therefore, equating these two quantities for constant radius, we see that E r dB by dt is equal to E by 2 pi r into d phi by dt, and therefore from this one can obtain the relation that the flux should be equal to 2 pi r square. To ensure that the electron moves in circular path of constant radius, the magnetic flux within the orbit of radius r should always be twice what it would have been if the magnetic field were uniform throughout the orbit. So that is what is represented by this condition. So the factor of 2 indicates this. Thus the orbital magnetic field should be half of the average field over the downward area. This is a condition which can be achieved by making the air gap in the central part of the magnet smaller than that in the air gap enclosing the circular orbit. So therefore, the magnetic field strength will be higher in the center as compared to the region enclosing the circular orbit. Let us calculate the energy gained by the electron. The particles have maximum energy when the magnetic field is at its strongest value. If the total energy is much greater than the rest energy, then we can write E is equal to P into C. This is a relativistic relation. The centripetal force is as usual provided by the Lorentz force arising from the magnetic field. So therefore, the momentum of the electron will be P is equal to mv, which is equal to EBR. So therefore, the energy can be represented as E is equal to BERC, where B is the maximum value of the field as at the point P here, that the maximum of the waveform. You can see that after P, the field starts diminishing. So at that point, the electrons are extracted from the betatron to fall on a target. Otherwise, what happens is that if this is not done, the magnetic field will start decreasing and it will no longer be possible to constrain the electrons in the circular orbit and accelerate them. Therefore, only 1/4 of the entire period of the variation of the magnetic field is useful for accelerating purposes. It is evident that the betatron also delivers pulsed electron beams. Of course, the relativistic increase of mass is not a problem at all for the betatron, since the betatron condition is independent of the electron mass. So it automatically satisfies the constraint arising from the relativistic increase of mass. However, as the beta ray energy increases, Bremsstrahlung radiation becomes appreciable and it will limit the maximum energy available to the electrons. So that is one disadvantage of the betatron. Another disadvantage, the large amount of the iron core required to generate the magnetic field in conformity with the betatron condition makes it bulky. So the betatron becomes quite bulky because of the large amount of iron core. The major bulk of the iron core is required for accelerating purpose, and only a small fraction is required for guiding the electrons along the constant radius orbit. So naturally, it would be better if the accelerating and orbiting guiding functions can be decoupled. A way out was suggested and developed by Macmillan and Wechsler. So that resulted in what is known as the electron synchrotron. The idea suggested by them was to accelerate the electrons by an RF cavity, which is very similar to the method in a linear accelerator or a cyclotron. The acceleration then could take place over a large number of cycles without appreciable loss in synchronism. The electron synchrotron consists essentially of a downward shaped vacuum chamber as in the betatron and a laminated iron core covering an annular area above and below the downward portion only. So thereby the amount of iron core can be considerably reduced. In the annular region where the electrons are moving, the field varies in exactly the same fashion as in the conventional betatron. However, The acceleration is provided by RF cavities at one or more locations along the circular trajectory. These cavities maintain standing electromagnetic waves with the electric field directed tangential to the trajectory of the electrons. So therefore, the electrons get accelerated within the RF cavity. In fact, the electrons move in the orbit with a velocity which is practically close to c. The RF frequency is chosen in such a manner that the electrons arrive at the RF cavity every time at a given phase of the electromagnetic radiation. So this is a schematic of the electron synchrotron. So these represent the laminated steel ring magnet. This is the donut shaped vacuum chamber. So we have an electron gun which is the source of electrons. Then at one particular location we have an RF cavity where the standing waves, electromagnetic radiations, accelerate the electrons. And this of course is the electron orbit. There is a unique feature and use of the electron synchrotron, which is the so-called synchrotron radiation. Now what is the synchrotron radiation? This is actually the electromagnetic radiation which is emitted by the accelerated electrons because they experience radial acceleration in the accelerator. So therefore, as the electrons are bent along the circular trajectory, the resulting acceleration will ultimately result in the emission of light, and this is called the synchrotron light. These are mainly used to atomic structure in the areas of chemistry, biology, technology, and condensed matter physics, etc. These are some of the relevant properties of synchrotron radiation, which was useful for many practical applications. The intensity is quite high. At the same time, the emittance is low. The spectrum of the radiation emitted will be continuous, and there is a pulsed time structured. The collimation can be excellent, and at the same time, both linear and circularly polarized light can be obtained. The continuous spectrum means there is a broad spectrum which covers from microwaves to hard X-rays. Then the user can select the wavelength required for experiment either with a monochromator or adjusting the emission wavelength of insertion devices. Another type of electron accelerator is the so-called microtron, which actually combines the features of a linac and a cyclotron. The electron gains energy from a resonant waveguide cavity and describes circular orbits of increasing radius in a uniform magnetic field. So the electrons get accelerated from the electromagnetic radiations in the waveguide, and they go in ever increasing radial orbit, and finally they will be extracted at the periphery. So there will be a magnetic field perpendicular to the plane of these trajectories. After each passage through the waveguide, the electrons gain an energy increment, resulting in a larger radius for the next pass through the waveguide cavity. A more recent development in accelerator field is the so-called production of radioactive ion beams. Here we use an ion beam which comprises of radioactive species rather than stable nuclei. In the normal accelerators, what we get is a beam of stable nuclei which are accelerated to the requisite energy. Now in the radioactive ion beam facilities, we get ion beams which comprise of radioactive ions. An obvious advantage for this is that we can access hitherto unexplored nuclei beyond the stability line near to the p proton and the neutron drip lines. So in these, the radioactive ions are produced in some suitable primary nuclear reaction. Then these are further accelerated in a second accelerator. So first we have a driver accelerator, and the accelerated ions bombard a target wherein the suitable reaction takes place, and the radioactive species are generated in that primary reaction, and they enter what is known as a fragment mass separator, which comprises of a suitable electromagnetic field, and the ion species that is required for the experiment will be separated, and then these are again further accelerated to the requisite energy, and thereby we get the radioactive ion beam. Now we come to the applications and uses of accelerators. Well, it's difficult to enumerate all the detailed applications and uses, but I will try to summarize the most relevant ones. Of course, the primary aim of an accelerator is to accelerate charged particles to high energies from keVs to TeVs. And then, why do we need to do that? We have to carry out nuclear reactions in order to probe into the nucleus and to determine its structure, properties, behavior, etc. So this is a simple nuclear reaction. We have an accelerated projectile which bombards the target X, and because of the interaction between these two, a residual nucleus Y is produced, and at the same time there is an ejectile which is an outgoing particle at some particular angle with respect to the incident projectile direction, and with energy which is decided by the kinematics. For example, here we have deuterium ions hitting a lithium 6 target and thereby producing 2 helium nuclei. Similarly, another type of reaction, a proton hitting a fluorine 19 nucleus and the subsequently an oxygen 16 nucleus and an alpha particle are produced. Such nuclear reactions result in the emission of radiations of particles. The ejectiles can be either particles like protons, neutrons, alpha particles, or heavier ions, or maybe gamma radiations. These radiations or particles emitted from the nuclei are very characteristic of the nuclei from which these are coming out. A suitable study of these radiations or particles will give direct information on the structure, properties and interactions of the nuclei. So that is the basic aim of carrying out any nuclear reaction. And for carrying out such nuclear reactions, we require an accelerated beam of ions. There are many applications in cosmology and astrophysics. Of course, the accelerators help in the understanding of the synthesis of the elements in stars, that is the nucleo-synthesis. So this will require the determination of the rate and cross-sections of several important nuclear reactions relevant for such cases. These are some of the light ion reactions which are responsible for energy production in the stars. Nuclear reactions in the laboratory at very high energies using these accelerators make it possible to recreate the extreme conditions of temperature and density that existed very soon after the Big Bang, the origin of the universe, and make it possible to study the various processes that followed the Big Bang. Another very important application is the determination of the elemental composition of various types of samples. In general, this can be called materials analysis by nuclear techniques. Now, some of the main experimental techniques which are routinely used for this purpose are the Rutherford backscattering, proton-induced X-ray emission, charged particle activation analysis (CPAA) or nuclear reaction analysis (NRA), and neutron activation analysis (NAA). All these techniques require accelerated beams of charged particles and well-defined energies, except of course for the NAA, which requires neutrons as the primary radiations. Now, radioactive isotopes are very important, not only for research purposes but also for many practical applications and in industries. For example, iodine-123 is a very important radioisotope which is useful for medical applications. So this is produced via the nuclear reaction 123 tellurium being bombarded with protons. A neutron is emitted in the process and resulting thereby the I-123 nucleus, which is radioactive. So these radioactive isotopes are produced via nuclear reactions. So we have a suitable nucleus which is bombarded with an incoming radiation, and it gets excited and it can emit various types of radiations or particles. We know that the primary radiations or particles which are emitted from radioactive isotopes are the alpha, beta and gamma rays. Now these radiations emitted from the radioactive isotopes can be used in a variety of applications in our day-to-day life as well as in several industries, medical field, etc. Now, in industry, radioactive isotopes of various kinds are used for measuring the thickness of metal or plastic sheets. Their precise thickness is indicated by the strength of the radiation that penetrates the material being inspected. So we have a source of radiation, and these are passed through the material being investigated, and the transmitted beam on the other side is measured, and this in relation to the intensity of the incident beam will give us a knowledge of the thickness of the sheet. So this is called a thickness gauge. They are also employed to replace large X-ray machines to examine manufactured metal parts, etc. for structural defects. This is the so-called industrial radiography. So we have again a source of radiation. This is passed through the material being investigated. So any deformity or structural defects on the surface or inside the material being investigated will be revealed in the sort of image which is taken on the other side. So therefore, from a study of these images, one can actually get information about the defects within or on the surface of the material that was investigated. Another significant application is the use of radioactive isotopes as compact sources of electrical power. For example, plutonium-238 is used in a spacecraft. So we have a schematic diagram which shows how this is utilized. We have the plutonium-238 source. These radiations are absorbed in a material, and thereby this will heat up one junction of the thermoelectric device, and that will produce a potential difference, and this can be passed through an external load. So in these cases, the heat produced in the decay of radioactive isotopes is converted into electricity by means of thermoelectric junction circuits or some other related device. Now, what are the medical applications? There are two primary roles for particle accelerators in medical fields. One is the production of radioisotopes for medical diagnosis and therapy, and as sources of beams of electrons, protons, and heavier charged particles for medical treatment. Cancer therapy with electron and photon beams, as well as with light and heavy ion beams. Conceived in the 1950s, proton therapy, where a tumor is bombarded with a beam of protons, remains one of the most cutting-edge treatment for cancerous tumors. These charged particles damage the DNA of cancer cells, thereby killing these. I just talked about the synchrotron radiation, which is produced in the synchrotron. So here the electrons are accelerated in the magnetic field to very high energy to emit a bright and coherent beam of high energy photons called the synchrotron radiation. They are mainly used to atomic structure studies in the areas of chemistry, biology, technology, and condensed matter physics, etc. So this is how the synchrotron radiation is produced. So the electrons move in circular orbits in the magnetic field. So because of the acceleration, they emit synchrotron radiation. There is a possibility that this can be highly focused. The intensity is quite high in a broad spectrum. The radiations can be polarized, and usually we get pulsed beams. Now, ion implantation is another important technique using the accelerators. What is done here? The implantation of accelerated ions at specific lattice sites of a semiconductor and the creation of defects is a highly developed technology. The depth of the implant is controlled by choosing the ion energy, which is usually between 2 and 600 keV. A large variety of semiconductor chips can be manufactured using this technology. Then accelerators can be used either directly or through the production of radioisotopes. They can be used for food preservation and sterilization. For example, these radiations kill the germs. So therefore, this can be used for disinfecting drinking water, the treatment of solid waste, then removal of noxious substances, treatment of waste gases, medical sterilization of medicines, surgical equipment, etc., and for preservation of food items. In particle physics, which is also known as high energy physics, we ask basic questions about the universe and its structure, constituents, etc. With particle accelerators as their primary scientific tools, a host of elementary particles have been discovered and their properties understood. So this is just a representative schematic showing the various types of elementary particles which have been discovered and understood by using particle accelerators. Also, particle physicists have achieved a profound understanding of the fundamental particles and physical laws that govern matter, energy, space, and time. Yet another recent and promising application of accelerators is in the accelerator-driven subcritical reactors for power generation. Here the primary source of neutrons is the spallation reaction on a heavy target. For example, 1 GeV protons on a lead target yields about 20 to 30 neutrons. So this is a schematic of the typical accelerator-driven subcritical reactors. So we have a spallation target similar to lead or some heavy target. This will be surrounded by a blanket assembly of nuclear fuel, such as fissile isotopes of uranium or plutonium or thorium, which can be breed to uranium-233. So in this way, there is a possibility of sustaining a fission reaction. So basically, we have the high energy, high current proton accelerator, which supplies the accelerated proton beam, and when this falls on the spallation target, spallation neutrons are produced, and these bombard the nuclear fuel and produce fission and generate energy. So this can be given to the grid for home consumption or industrial consumption, and a small fraction will be fed back to the accelerator for sustaining the accelerator. In such a system, the neutrons produced by spallation would cause fission in the fuel, assisted by further neutrons arising from that fission. Up to 10% of the neutrons could come from the spallation, with the rest of the neutrons arising from fission events in the blanket assembly. So the entire blanket assembly is a subcritical system, and therefore there is no danger of the system becoming supercritical and resulting in an explosion. The moment we withdraw the accelerated beam, the reactor will stop functioning. So therefore there is no question of going into a supercritical system. So from the safety point of view, this is good. I will end this video at this point. I'll be back soon with yet another video on basic principles in physics. Till then, goodbye.